So this was requested by a student. He wanted to see me sort of work through the examples or the problems in the written assignment. So this is homework 6, and if this seems helpful, then I'll keep doing it every week for the new homework. So let's start. Let's call this homework 6 solutions. Oh man, it's going to take me a little bit to get used to this new thing that I have. So just bear with me. Okay. And the handwriting is going to be awful. So homework 6 solutions. All right, not so bad. All right, reasonable place to start is number 1. Okay. And this is part A. So we have the limit as x goes to infinity of ln of x squared all over x. Okay, so just plugging in, which is the first thing we should always do, we get infinity over infinity, right? ln of x approaches infinity as x goes to infinity. And of course, x goes to infinity as x goes to infinity, right? This is easy. So the form is correct to use L'Hopital, and I'm just going to put an equals with an h over it to signify when I'm applying L'Hopital's rule. So we have limit as x approaches infinity, and I take a derivative on top and bottom, right? Remember, this isn't the quotient rule, it's what you would hope the quotient rule would be. So I apply chain rule to the top, which is 2 ln x times the derivative of the inside, which is the derivative of ln x, or 1 over x. Derivative of x, that's something we're certainly comfortable with by now. That's just 1. All right, simplifying and carrying my limit through so I don't forget about it, I get 2 ln x over x. This is just moving this x down to the bottom. Great. Okay, we've applied and we've simplified. So let's try again. We plug in and we get infinity over infinity. Okay, that just means we have to apply L'Hopital again, but that's not a problem. So I'll write my equals h, and I take a derivative of the top and the derivative of the bottom. Derivative of the top is going to be 2 over x. Derivative of the bottom, again, it's just 1. This is the limit as x approaches infinity of 2 over x, which of course is something we've dealt with before. This is 0. I have something fixed on the top like a 2 and something going to infinity on the bottom. Great. On to part B of problem 1, I have the limit as x approaches 0 of sine 3x over 2x. And first thing I do when I see a limit is plug in. In this case, I get 0 over 0. Great, that means I can immediately apply L'Hopital's rule. So I do just that. Ooh. Get rid of that. Nope. I apply L'Hopital's rule. I take the derivative of the top. That is a chain rule. 3 cosine 3x all over 2. And I evaluate again. Plug in 0, and cosine of 3 times 0 is cosine of 0. That's just 1. So this sum is just 3 halves. Nice and easy. Part C. This one I have the limit as x approaches infinity of square root of x times e to the minus x. Okay, so I evaluate again. as I always should. I plug in infinity, I get infinity in the first term, and then e to the minus x. Remember that the graph of e to the x looks like this. That's pretty good for, I'm using the stupid pad thing. So I'm still new to it, but this is, that's not bad. I'm proud of myself, okay? If I plug in infinity into e to the minus x, this is really just asking the question, what happens to e to the x as x goes to negative infinity, right? So I'm just taking the infinity and putting a minus up front. So as I go to minus infinity, what happens to e to the x? Well, it approaches 0, right? This is just from looking at the graph, this is something you should know. So I have infinity times 0. And this is an indeterminate form, something like we've seen. But the problem is I can't immediately apply L'Hopital's rule. What I have to do is, turn this into a fraction of some kind. So that's what I'll do. And there's sort of an obvious way to do this. Just because I have a negative exponent that's sort of screaming at you to move it down to the bottom. So we'll listen to it, and we have square root of x over e to the x. And we're taking that limit as x goes to infinity. Now plugging in, I get infinity still out of the square root of x. That hasn't changed. But now I'm looking at the limit as x goes to infinity of e to the x. And coming back over to this graph, I have that it goes up toward infinity. So I get infinity over infinity, which is an indeterminate form that I can work with, something that L'Hopital applies to. So I will go right ahead and apply L'Hopital. On the top, I get the derivative 1 over 2 square roots of x. And on the bottom, nothing changes. This is just e to the x. All right, well, I don't quite want to plug in yet. This is a little ugly. I'd rather it just be one fraction and then try to plug in. So we'll simplify a little. I keep my limit. And I have 1 over 2 e to the x square root of x. Now if I plug in infinity, I have 2 times something going toward infinity, e to the x goes toward infinity, times something going toward infinity. So this is 1 over 2 times infinity times infinity. Now, if you remember from class, infinity times infinity is not indeterminate, right? Infinity times infinity is, well, infinity, because it's a huge number times another huge number. It's just going to get even bigger. So I have a fixed number over something going toward infinity. I know what that is. It's 0. All right, so for part D, limit as x goes to -1 of x to the third, handwriting's a little small here, plus 6x squared plus 11x plus 6. That's all on the top. And on the bottom, I have 2x cubed plus 13x squared plus 26x plus 15. Extend that a little bit. Okay. All right. Now, especially with something like this, I definitely want to be careful and make sure that I plug in. If it's something that looks like a L'Hopital's problem, then you could probably get away with not checking. You still will probably lose a point or something. But it's harder to trick when there's something that looks like a L'Hopital's problem. This, however, looks like something that you can just plug in and get an answer to. So we need to really, really check and make sure that we get something that's indeterminate. So if I plug in -1, I want to see what I get. -1 cubed, 13 -1 squared, plus 26 times -1, plus 15. And sorry, again, for the handwriting. I know it's not the best. So -1 cubed is -1. -1 squared is just 1, so I just get a 6 here. So this is -1 plus 6 gives me 5. And then I have a -11 plus 6. That's a -5. So I have 5 minus 5. That gives me 0 on top. Okay, looks like L'Hopital so far. But it could be just a number on the bottom, so we should double check. 2 times, again, -1 gives me -2. Plus 13 gives me 11. And then I have a -26 plus 15. that's going to be negative 11. So I have 11 minus 11, which of course is 0. Okay, so L'Hopital does apply, and we have to go through that. It's not just as simple as plugging in. Okay, so derivative of the top, this is pretty straightforward. It's all just power rule. So we get on the top 3x squared plus 12x plus 11. And on the bottom, I get 6x squared plus 26x plus 26. And we'll try to plug in. If everything works out right, then we won't have to do this again. We get 3 times negative 1 squared plus 12 times negative 1 plus 11 divided by 6 times negative 1 squared plus 26 times negative 1 plus 26. Great. I get a 3 here. Minus 12 gives me minus 9, I believe. And that gives me, when I add 11 to minus 9, it gives me 2. Then I have 6. And over here, I have a minus 26 plus 26. So this just goes to 0. So this is just 6 on the bottom. So the answer here is 1/3. And notice, I mean, this was a mistake that was on the exam, but you know, it's been a little while, and with all the distractions, it's understandable to forget sort of the conventions of this thing. But notice I'm carrying my limit through right up until I plug it in. Once I've plugged in, this is me evaluating the limit, right? It doesn't make any sense to drop, for example, if I had sine of pi over 3, right? This is not the same thing as pi over 3. But dropping the limit is the same thing as dropping sine, for example, right? So this is not the case. However, me saying that sine of pi over 3 is equal to root 3 over 2 is not me dropping the sign. It's me evaluating the sign. And that's exactly what I've done, right? I'm carrying the limit through until I've evaluated it. And me evaluating it is just plugging in. So all I'm doing here is evaluating this just as I'm evaluating sine. Maybe that explanation helps, maybe not. Question 2. All right. This is more limit work, but a little bit more complicated. This one is one that I believe we did in class. At least I did with my section. I don't remember if the lesser Nick covered it in his. So evaluating, again, the first thing we should do is plug in. So sine of 0 is 0. Great. What's the ln of 0? Well, for this, again, we need to return to the graph. So remember that the graph of ln of x is something like this, where this point here is 1, which means that the ln of 1 is 0. And as I approach this, this is f of x equals ln of x equals, yeah. As I approach 0 from the right, and notice we were careful to have the plus sign here. As I approach 0 from the right, I approach this vertical asymptote, meaning that this thing dives down to negative infinity. So this is of the form 0 times infinity. The negative isn't important here. So this is something I can apply L'Hopital to, but not quite yet. I have to massage it a little. I have to turn it into the right form. So for this, we use the standard trick. And in this case, it turns out that leaving ln of x on the top is the easier way to do this for whatever reason. I don't really have a great explanation for it other than it just is. But maybe one way to see it is that I can write 1 over sine, right? Remember, this is the same thing as, remember my limit. This is the same thing as turning it into 1 over sine on the bottom, right? 1 over sine is the same thing as cosecant. I'm just sort of writing it in a condensed version here because it's a little bit easier to take a derivative written this way. But this is really what I'm doing, and this is the standard trick. Right. Okay, so now I have this, and what is the form? I'll write it over here. ln of x as x goes to 0, again, is infinity, negative infinity, but negative doesn't matter. And as x goes to 0 of cosecant of x also turns out to be infinity. And this is easy to see by looking at cosecant as 1 over sine. So this is 1 over 0. And as 0 approaches from the right, this approaches infinity. Okay, so this is something I can apply L'Hopital to. And we'll do just that. So the derivative of ln is 1 over x. That's a standard one. I'll make that bar a little bit longer. The derivative of cosecant, that one's a little bit harder to remember, but it's negative cosecant x cotangent of x multiplied together. Okay, so this is maybe better, maybe worse than what we had. Let's take a look. Let's try to clean it up just a little. I have 1 over, well, let's put the negative up here. I'll move this negative up to here. X cosecant x cotangent x. Okay, now it's not clear to me, I really don't want to deal with these things like this, cotangent and cosecant. These are sort of the weird trig functions. So my idea with this is maybe to translate it into sines and cosines, just so I can evaluate and figure out what's actually going on. So I have x times 1 over sine x. And again, apologies for the handwriting there. And then remember, cotangent is cosine over sine. Sine. Okay. All right, I can simplify that a little. I have negative 1 over x times cosine of x over sine squared of x. Okay, and then dealing with this and rewriting it as a big fraction, as one big fraction, it turns into negative sine squared of x over x cosine of x, right? Because I have a fraction on the bottom, and you can just move the x up to the cosine term here. Remember that I have the top divided by the bottom means that I take the top, flip the bottom, and then multiply, right? So I just sort of bring that guy up there, and I have my negative sine squared. Okay, now there's one more trick I want to do, and that is splitting this up and breaking off the piece that I already know the answer to. What do I mean by that? Well, negative sine squared of x over x is not something I know the limit of quite yet, because this is going to be of the form, let me see if I can do this, 0 over 0. Terrible quote marks, but okay. This is of the form 0 over 0. But I know what the limit as x approaches 0 of 1 over cosine is. And it's because I know what cosine of 0 is. This thing, it's just equal to 1. So essentially, I can just ignore this from my limit computation. And now I just have to worry about evaluating this, which is certainly a little bit easier, right? It's a lot less of a pain to deal with this derivative, because even here in this form, it's still 0 over 0. But taking the derivative of the bottom is not really ideal. Okay, so now I have the form, again, like I wrote over there, 0 over 0. Okay, I apply L'Hopital to this. And what do I get? I get negative 2 sine x cosine x. Because remember, that is a chain rule. I have to do the squared part first, bring the 2 down, leave the inside the same, and then multiply by the derivative of the inside being sine. And the derivative of x is just 1. So I can just evaluate again because there's not really any simplification here. You can rewrite it without the 1, but I'm starting to run out of room, so I won't do that. Plugging in 0, I get -2. That stays the same. Sine of 0 is 0, and cosine of 0 is 1. I have 2 times 0 times 1. 2 times 0, -2 times 0 times 1, or simply 0. Okay, moving on to question B. It turns out that we did basically all the heavy lifting that we need to do for part B already. So we want to compute the limit as x approaches 0 from the right of x to the sine of x. Now, remember that the trick here is to set this thing equal to y. And what's y? Who cares? It's just some variable. Some dummy variable here. Right? The reason is because I want this to hold the information of the things that I'm doing to this. I want to remember that y is the thing I want to solve for, right? Because I'm going to take a natural log of both sides here, and it's very tempting to want to solve for the natural log limit and stop there. But you have to remember that y is the thing that you want to solve for. So I'm going to carry this y through the whole time, and you'll see why that's important at the end. So taking the ln of both sides, and of course the reasoning for this is because I want this thing to come downstairs so I can play with it, right? Because this is of the form this is of the form 0 to the 0. And again, that's an indeterminate. We're not sure what that is. That could be anything. So as x approaches 0 from the right, I have the ln of x to the sine of x equals the ln of y. And I'm going to keep this as a two-sided thing the whole time. Limit as x approaches 0. I'm just applying the log rule here. I bring your mom down. Those of you in my class will understand that. Those of you in next class are going to wonder what the hell I'm talking about. I'll keep that as an inside joke, though, for my students. Now I have the limit as x approaches 0 from the right. Pretend this is x approaches 0 from the right, and then I can actually write like a human being, of the sine of x times ln of x. Right? This is the limit we just computed. Right? So from A, this limit is equal to what? What did we get? 0, I think, right? 0. So I have 0 equals ln y. Great. Okay. Now I'm at this point, and had I had to do all that work in between, it would have been very tempting to say, okay, 0 is my answer, box it. That's not the case, however, because y, i.e., the limit as x approaches 0 from the right of x to the sine of x, is the thing that we want to solve for. We've solved for the ln of this thing. So we just need to show y is e to the 0, right? Remember, I have, crap. Where's that? We have these arrows because I have a little implied e down here. This is my base. E raised to the 0 equals y. This is sort of how I remember this thing. So e raised to the 0 equals y, and anything raised to the 0, except for 0, right, is equal to 1. So this is my answer. And on an exam or something, it's totally fine to write y equals, as long as you define y clearly up here. Moving on to question 3. I have the limit as n approaches infinity of 1 plus 0.02 over n raised to the nt. Okay, again, I have a limit which involves n. I have n downstairs in this whatever expression, and I also have n upstairs in the exponent. When I have something of this form, use your placeholder, right? If it's something you can't evaluate, right? Of course, I should be plugging in each time. But 1 plus this as n goes to infinity ends up going to, well, this goes to 0, so this is 1. And then n pulls t to infinity because t is just a constant with respect to this problem. So this is 1 to infinity, and again, that's an indeterminate form. That's something that we've seen. So I want to set this equal to y because I want to take an ln to bring the nt downstairs. So we'll do just that. We'll take the ln of both sides. And of course, you could just do this in one step. You can just bring the nt down. You don't have to write it out like this, but I'm just doing it just to be clear. Nt times ln of 1 plus 0.02 over n equals ln y. Great. Okay, now this is where a lot of students struggled. Notice that when I apply L'Hopital, I'm only taking a derivative with respect to this variable here. It's only with respect to the limit variable that I take a derivative. What that means really in respect to this problem is that t is a constant, right? T is completely unaffected by this n going to infinity. So a nice way to do this is to rewrite this as t times this limit, right? I can pull the t right out of the limit. And now this is something that we've seen almost exactly before, right? Okay, so I have my t still floating around. And I need to rewrite this thing because I have the form here, infinity times ln of 1 plus 0. And remember that ln of 1 is 0. So this is infinity times 0. So my general feeling about these is that if I have an exponential indeterminate form, that is sort of the worst case scenario. The first thing I have to do is make it a little bit better. I can't make it perfect yet, but I can make it a little bit better. The little bit better is this, a multiplicative or a product form of an indeterminate form. And then the final step is to turn it into a quotient, something I can do L'Hopital to. So I think the obvious decision I should make here is to put 1 over n on the bottom, right? This is the standard trick, and I definitely don't want to put 1 over ln of that mess on the bottom. That would make a derivative way too difficult. Okay, so I will move up here because I'm starting to run out of room. So I have t times this, and now I'm applying L'Hopital's rule. So what is the derivative of the top? It is 1 over the thing on the inside times the derivative of the thing on the inside, which is negative 0.02 over n squared. And you should check that for yourself. But it's just an application of chain rule there. And on the bottom, I get negative 1 over n squared. Now, how I'm going to write this here is I'm going to put my h here. Why do I put my h there? Well, what I've done is I've taken the derivative of the top and the derivative of the bottom here. And I can say that this is equal to ln of y, meaning equal to this original limit here because of L'Hopital's rule. L'Hopital says if it's in this form, you can take a derivative of the top and the derivative of the bottom, and it's still equal. So this thing is equal to ln y, which is then equal to this by L'Hopital's rule. So this is the way I write this. Okay, now we just simplify, which I know for most of you is sort of the hardest part. On the bottom, I have a fraction. So remember that I take the top, flip the bottom, and multiply. Right? This n squared comes up and becomes the top part of this. So it's going to cancel with this n squared. So I have n squared and n squared going away, negative and negative going away. And I'm left with just 0.02 over 1 plus 0.02 over n. And this still equals ln y. I'll finish off my end there. Okay. All right. Now I evaluate again. Still have the t, unaffected by the limit. Oh, nope. I want to evaluate the limit now. And I get 0.02 over 1 plus 0.02 over infinity. I have something fixed over something going to infinity. This whole thing goes to 0. Goes to 0 in the limit. It's not equal to 0, but it goes to 0. So that's over 1. Still equals ln y. I'm carrying through my ln y to remind myself that I have to exponentiate after. So really what I have is, flipping the order just to see it a little bit clearer, is 0.02 t equals ln y. Following the arrows again, I get e to the 0.02 t equals y. And that's the thing that we're after. All right, now let's move on to number 4. And again, I'll apologize for the horrible numbers. I didn't realize. I think I stole this right from the book, and I assumed that the numbers would be cleaner. So I hope you were able to find a calculator pretty easily. I found one pretty quickly online. But what we want to do here is find and classify the critical points. So let's find them first. That'll be like step 1. So what I do is I take a derivative, and I set it equal to 0. And really, usually, sometimes there's like an or infinity. You'll see me write that sometimes. This is just to take care of the case where there may be a problem with the domain of the derivative. But here, there's no fractions, there's no square roots or anything, so we don't really have to worry about this. All right, so this does not factor nice, and again, I apologize for that. But it ends up factoring into, well, it ends up giving solutions of this, which simplifies to something which is a little bit nicer to deal with. Crap. That I want fraction. -1 plus or minus square root of 33 over 3. Okay. So these are the locations of critical points. Remember that critical points are ordered pairs. So I need to actually find the critical points. What I mean by that is I need to find f of -1 plus square root of 33 over 3 and f of -1 minus square root of 33 over 3. And these are just going to be estimates. Because of course the numbers are horrifying and I messed up. So what I get here when I plug it into a calculator is 95.958 approximately. And here I get 124.042. Again, approximations here. Okay, so my critical points are going to be -1, oh crap, -1 plus square root 33 over 3, comma 95.958. About estimates good enough here. On an exam, these will be exact values for sure. And then the negative version with 124.042. Okay, so these are my critical points, and I want to find out, are they mins or maxes? And the two ways I need to do this are by the first and second derivative tests. So save that, clear that. Okay. So this is first derivative test. What I need for this is a number line, and I want to label the points that I have, -1 minus square root 33 over 3. And this one is -1 plus square root 33 over 3. Okay, so I like to use a table here. It sort of helps organize my work. So I have intervals, test values, my evaluation. And I'll leave a little bit extra space for that because that's a little bit more work. And then what is the sign that corresponds to that evaluation? And I'll explain this in a second here. Oh, clicking on stuff. Okay, so I need an interval, which is to the left of this guy. Well, what I mean by that is negative infinity to -1 minus square root 33 over 3. I need this one to be the in-between one, and I am not going to have enough space for this, but it's fine. You guys know what the points are. 3, it's plus. And this guy is plus. Pluses are not coming out well. To infinity. Okay. These are the 3 intervals I have. Had I thought more ahead, I would have made that a little bit bigger, but fine. I need a point in each of these. Now, if you think about it a little bit, -1 minus square root 33 over 3 is a little bit greater than -3. So an example of a point which lives in here is -3. To be safe, you can pick like -4 or -5 or something like that. But I'm just trying to pick sort of the smallest possible numbers I can. In between here, clearly 0 lives here, right? Because this is definitely bigger than 1. So -1 plus this is going to be bigger than 0, and this is definitely less than 0. So x equals 0. And up here, we can pick x equals 1 for similar sort of reasoning. This is about 0.9 something. Okay, so now I want to evaluate f prime, right? I want to evaluate the derivative at these points. So I have 3 times -3 squared plus 6 times -3 minus 8. And here I get 1. So that's a positive. So I'll put a positive on that interval. That means that on this interval, the function is increasing. Over here, I have 3 times 0 plus 6 times 0 minus 8. That is just minus 8. It's clearly negative. So it's decreasing on that interval. And here I get 3 times 1 squared, right? Squared. Plus 6 times 1 minus 8. 3 plus 6 is 9. Minus 8 is 1. Positive there. Great. Okay. So I have increasing before this critical point, decreasing after this critical point and before this one, and then increasing after the second one. So that tells me that I have and what was the number corresponding to this? This is 124.042 is a local max, right? Because it's decreasing or increasing before and then decreasing after. And -1 plus square root 33 over 3, comma 95. Try to do it from memory, it didn't work. 95.958 is a local min. Great, so we found and classified the critical points according to the first derivative test. Now let's do it by the second derivative test. All right, so of course for the second derivative test, I need a second derivative. So I'll just compute this really quick. It is 6x plus 6. Great. And for this, I want to just evaluate each of these x values. So I'll do -1 minus square root 33 over 3. And I get what? I get 6 times this thing. This is actually something I can do by hand, it looks like. Because I get -6. 6 divided by 3 gives me 2. So I get -2 square root 33 plus 6. Okay, well, -6 and +6 cancel. I get -2 times root 33. And that's certainly less than 0. Okay. Therefore, -1 minus square root 33 over 3, comma, 124.042 is a local max. All right, same kind of thing for this. I get -1, and my battery's starting to die on my laptop. This is starting to lag a little. Actually, let me pause this. Okay, sorry about that. My laptop died. So let's now do the same thing for the other critical point. Pluses are just not coming out there. So again, I get 6 times -1 plus this time, 33 over 3 plus 6. Okay, I still get my -6, but this time I get a plus 2 root 33. Oh, clicking on stuff. 2 root 33 plus 6. Okay, so my +6 and my -6 still go away, and I get 2 root 33, which is certainly greater than 0. Therefore, -1 plus root 33 over 3, comma, 95.958 is a local min. As expected, right? We get the same answer for first derivative and second derivative test. They will give you the same answer. And in fact, it looks like in this case, because it doesn't factor, because the first derivative doesn't factor well, this is probably the easier way to do it, right? So this was, a question that I received in lecture. Why do we need both? It just turns out that some problems are easier to do this way, some are easier to do this way. I generally prefer the first derivative test, but there are definitely times when the second is called for. Okay. And finally, we're moving on to problem number 5. So this is the same function, and I'll rewrite it out so we have it. Where is it? F of x equals x cubed plus 3x squared minus 8x plus 100. Okay, and I'm looking for, this is, in this case, on the interval -3 to 0. Okay, so it's the same function as before, and I'm looking for absolute mins and maxes. But really, they're unique, so I should probably just say right, there's only going to be one absolute min and one absolute max. Okay? So we need to figure out the candidates, right? What are the candidates? In general, candidates are critical points and endpoints. Okay, so we need to, first of all, worry about being inside this interval, right? We have critical points that we found already, but maybe both of them aren't in here. And it is actually the case. Notice which one is in there. Notice that -1 minus square root of 33 over 3 is in -3 to 0. And you could do this by checking on a calculator, right? This is about 2.9, so it's just inside the interval. But -1 plus square root 33 over 3 is not. Okay, so this is important. This is not a candidate, right? Not a candidate for being an absolute min or max because it's not on this interval, right? We're restricting our attention to -3 to 0. So the candidates are, I'll put this in parentheses, candidates are -1 minus square root 33 over 3, comma 124.042. And again, this is just an estimate, right? Ballpark, but it should be good enough for our purposes. And then the endpoints. Well, the endpoints I'll compute over here. I need to evaluate what's f of -3. And this is, it turns out to be, I won't go through all the work, 124, exactly 124. And f of 0 ends up being 100. That one's a little bit more clear. This one requires a little bit of work, but not too much, actually. I just don't want to eat up so much space. So my candidates are -3, 124, and 0, 100. Now, for absolute min and max, it's even simpler than local min and max. I don't need to check derivatives. I don't need to check first derivative test. I don't need a number line. I don't need a table. All I have to do is focus on the outputs, right? I want to find out what is the highest this function goes and what is the lowest this function goes. Of course, restricted our attention to this interval. So in this interval, these are the only candidates I have to look at. And it's just a matter of comparing these values. So just by inspection, the absolute max, I'll separate this out so I don't run into it. The absolute max is the one that gives us the highest output, namely the one that gives us 124.042. It's a slight difference, right? There's definitely it's only a small difference, but this is certainly bigger than 124. Even though it's an estimate, we know it's definitely bigger than 124. This is exact. And the smallest, and the absolute min, is 0, 100. 100 is the lowest this function goes.